We start talking about units. Units of measurement. If you think about it, all units are made up, aren't they? You know where the unit foot came from? It was the length of a man's foot. And when they realized that, oh, maybe we need to be a little more precise than that because some guys have little feet and some guys have big feet, I think they went with the king's foot. And the king's foot was so long, and that's what they used to measure. So all units have this sort of a crazy, random, arbitrary nature to them. And so when we start making up new units, it sounds maybe a little flippant, but it isn't because they're all made up. In chemistry, we use units to measure things, and the units are critical. They're very, very important. And one of the biggest mistakes students make is just leaving the units off of their measurements. Oh, well, I'll remember what that was. There was a big problem in the space with NASA. NASA, they developed this, I think it was a Mars orbiter, and one group was doing calculations with English units, inches and feet, and another was using metric units, centimeters and meters. They didn't communicate well, and because of that, this very, very expensive spacecraft was designed wrong. And they launched it, and it started to orbit, but it was too close, and it got pulled in by gravity and burned up over a miscommunication about units. Units are really important. So the two most common unit systems in the world are the metric system, which most of the world uses, and the English system, which we in the United States use. Americans, we just have to do things our own way, don't we? And it's not always the smart way. The English system really is inferior to the metric system. And we keep saying that we're going to switch, and then we don't actually do it. But scientists use a system called the International System of Units, SI units, and it's SI instead of ISU because it comes from the French. I'm not even going to try to pronounce that because I took Spanish in high school. I didn't take French. The SI system is almost the same as the metric system. The units are exactly the same. The only difference is what they call the base unit. And so for the purposes of this class, and in my opinion, I don't care about the difference between SI units and the metric system. They're basically interchangeable. There is a very slight detail that makes them different, but we're going to ignore that because it just really doesn't matter. We are going to use the metric system. So please do not record the length of a test tube in inches. I will laugh at you, probably out loud. I might even take a picture of it and post it on Facebook, without your name, of course. But look what my student did. Right? No English units. So these are the SI base units. Length, we use the meter. The symbol is a lowercase m. Details matter. Okay, if you go on Mastering Chemistry and you type the course ID in and you get one letter wrong, do you get the right course? No. If you send an important email to your boss and you type in the email address and one letter is wrong, does your boss get the email? No. Details matter. Okay? So these abbreviations have to be exactly right. It's a lowercase m. It's not a capital M. It's not M period. It's not ME or MTR. We can't make up our own abbreviations. We all use the same. So for mass, kilogram, abbreviated kg. Time is in seconds. We're familiar with seconds. We use that even in the English system. The abbreviation is S, not SEC period. It's just S. The unit of temperature is a Kelvin, and that's a capital K. It's not a degree Kelvin. It's just a K. Amount of substance is in moles. The abbreviation for mole is MOL. I think that's dumb. Why have an abbreviation when you're just losing one letter? You have a question?
Yes, really fast. For the mass,
Mm-hmm.
why isn't it just gram?
That's a good question. Why isn't the base unit gram? In the metric system, the base unit is gram. In the SI system, the base unit is kilogram. And that's one of those little tiny details where, there could be, some instructors really get off on that difference and they'll ask, what's the base unit of mass in the SI system? And you have to know it's kilogram. I don't care. I don't care. But this is what the SI system says. And then they have base units for electric current and luminous intensity. We're really not going to get into those units in this class. This is a table in your textbook. Good to refer to sometimes. So let's talk about a couple of these units. The meter. It's important to have a concept of how large these metric units are, because most of you grew up measuring things in inches and feet and yards and miles. But it's important to have an idea of how long a meter is. A meter is roughly the same as a yard. So think of a yardstick. A meter is 3 inches longer. So I want you to know that. There are definitions, and they're very, very detailed. It was originally 1/10,000,000th of the distance from the equator to the North Pole through Paris, France. Wow, that's kind of random. Now it's defined as the distance that light travels through a vacuum in a certain period of time, which is this amount, this fraction of a second. Do you need to know that? No, you don't. What you need to know is that a meter is a little longer than a yard. This is a conversion factor, and we'll talk about those, but you don't have to memorize that one. I'll let you know what you need to memorize. Mass. So kilogram is a unit of mass. Mass is slightly different than weight. Mass is a measure of the quantity of matter. The weight of an object is a measure of the gravitational pull on the matter. And so weight depends on the force of gravity. So if you go to the moon, your weight is different. Your mass, though, is the same. As long as we stay on this planet, we can use weight and mass interchangeably. Anybody planning to go into space this semester? No, I didn't think so. So we're not going to get hung up on that, but there is a difference. So the SI unit is a kilogram. A kilogram is just a little over 2 pounds. So it's just a good idea to have an idea of how large that is. The common unit of mass, the one we use the most in chemistry, is the gram. And a gram is 1/1000th of a kilogram. And we'll talk briefly about the metric system and what these silly prefixes mean. They're not silly, they're awesome. Second, I think we're all familiar with how long a second is. 1/1000th, bang, there was a second. So it's abbreviated S. It's actually defined very specifically. The time it takes for a specific number of radiation events of a particular transition that occurs in cesium-133. We have these very precise definitions so that people in different parts of the world can make sure that their meter, their second, their kilogram is the same as our kilogram. Kelvin. Kelvin is the unit of temperature in the SI system. We talked a little bit about energy and about states of matter and how atoms and molecules are always moving. The temperature of something is a measure of the average kinetic energy of the atoms or molecules that compose that matter. So in the solid state of students, I'd say right now your temperature is pretty low. You're all kind of chill, right? You're relaxed, you're just sitting here. Now, if we all got antsy and wiggled around or started chair dancing or something, that would be like the temperature going up because the particles are moving faster. Temperature is a measure of average kinetic energy of the particles. Temperature determines which direction heat will flow. More fancy, it's called thermal energy transfer. thermal energy will go from a higher temperature to a lower temperature. And we know that by experience. If you put a warm can of soda in a bucket of ice water, what happens? The ice starts to melt and the soda gets cold, right? It would be weird if you did that and the soda got hotter and the ice water got colder. That just doesn't happen. Thermal energy goes from a higher temperature to a lower temperature until they get to be about the same. So let's look at temperature scales. So we are probably most familiar with the Fahrenheit temperature scale. And that's a very old temperature scale. Water freezes at 32 degrees Fahrenheit. Water boils at 212 degrees Fahrenheit. Kind of random numbers. The Fahrenheit scale is part of the English system, where we have 12 inches in a foot and 3 feet in a yard and 5,280 feet in a mile, and all these just kind of random numbers, right? So here we have 212 and 32. The Celsius scale, which is sometimes called the centigrade scale, is a metric temperature scale. And it's the one that we actually use the most in chemistry, even though it's not technically an SI scale. The Celsius temperature scale is based on the freezing point of water and the boiling point of water. And so the freezing point of water is assigned a temperature of 0 degrees Celsius, and the boiling point is assigned a temperature of 100 degrees Celsius. In between, there are 100 Celsius degrees. In between those same two temperatures on the Fahrenheit scale, there are 180 degrees Fahrenheit. So the Celsius scale is a very, very useful scale. The Kelvin scale came about because of an idea of absolute zero and through studies of gases and the relationship of their temperature to their volume. Absolute zero is so far a theoretical temperature at which molecular motion virtually stops. So that, solid state of students, we all moved so slowly that we stopped breathing, our hearts stopped beating, nothing moved. Of course, there are scientists that are trying to get something that cold. They've gotten really close. Nobody's gotten to zero yet. The Kelvin scale takes zero. See, on the Celsius scale, 0 is freezing point of water. The Celsius scale takes 0 and says that's absolute zero. It looks a lot like okay, but it's 0 Kelvin. Takes that to be 0, and then the temperature divisions are the same size. So 1 Kelvin is the same size as 1 Celsius degree. They're just offset. So here 0 is absolute 0, and in Celsius scale, 0 is the freezing point of water. So on the Celsius scale, water freezes at about 273 Kelvin. 100 degrees above that, 100 kelvins, pardon me, these are not degrees, they're just kelvins. 100 kelvins above that, water boils at 373 Kelvin. Yeah, so I got ahead of myself like I often do. I said that, I said that, said that. Here are the formulas that allow us to convert between the temperature scales. If you have a Fahrenheit temperature, you subtract 32 to compensate for the different 0 points, and then you divide by 1.8, and that takes care of the fact that the degrees are different sizes, and that will get you a Celsius temperature. Kelvin and Celsius are easier to interchange. You take the Celsius temperature and you add 273.15, and that will get you the Kelvin. If you have Kelvin and you want Celsius, you just need to rearrange the equation. If you have Celsius and want Fahrenheit, you need to take this equation and rearrange it. Those are equations that it would be good for you to memorize, especially the Celsius to Kelvin one, because we do that conversion a lot. So let's do an example. Gallium is a solid metal at room temperature, but will melt to a liquid in your hand. It's really, really cool to take a piece of metal, it's hard, solid metal, stick it in your hand, and as it warms up, it melts. It's crazy. The melting point of gallium is 85.6 degrees Fahrenheit. What is this temperature on the Celsius scale and on the Kelvin scale? So to do a problem like this, we need to use these equations, right? So Fahrenheit minus 32 divided by 1.8. Let's get a decent color here. So degrees Celsius equals Fahrenheit temperature minus 32 divided by 1.8. Sometimes my decimals look like commas. I want to make sure that they're seen, and scientists rarely use commas in numbers. So if you're not sure, assume it's a period. And then the other one is Kelvin is degrees Celsius plus 273.15. So the first question A, converting this to Celsius, we're going to just put this Fahrenheit temperature in 85.6 minus 32. Oh my goodness. I'm out of practice. I'm making all of this far too large. I guess the summer is longer than I thought it was. And I left my calculator in my bag. You should always bring your calculator with you to class. And when I do calculations, pull it out and do them with me, because I make mistakes. And a lot of people find it's very amusing to catch me in mistakes. You go right ahead. It doesn't hurt my feelings. So in degrees Celsius, my calculator is showing me 29.77 repeating. And that would be degrees Celsius as the unit. We're going to talk about significant figures and rounding things off and stuff. But what I'll tell you for temperatures, the best thing to do is to look at your original temperature. This is 0.6. It has 1 decimal place. So then when you convert this to Celsius, it should have 1 decimal place as well. And so we're going to call this 29.8 degrees Celsius. And that would be our best answer. Any questions? Going to Kelvin is even easier. We'll take the 85. Well, we can't start with 85.6. We need this number that we started with here. I'm going to use the unrounded version, and I'll explain to you in a minute why. So 29.77 plus 273.15. My calculator shows me 302.9277 repeating Kelvin. Again, I'm going to look at the original temperature that I started with. It had 1 decimal place. I am going to round my answer to 1 decimal place. So 302.9 Kelvin. So that's the answer to B, and the answer to A is squished in down here. The unit is part of the answer. It's not correct without the unit. Any questions? So in Appendix 1A is a review of scientific notation. the prerequisite you had to take for this class should have covered scientific notation. If you're rusty on it, go back and review. I'm not going to take lecture time to cover scientific notation. We are going to talk about the metric system a little bit, the prefix multipliers. So in table 1.2, which is this guy right here, in table 1.2, it lists the prefix multipliers along with that are used with standard units. And these multipliers basically are an abbreviation for a power of 10. They just stand in for the power of 10. So the example here is kilometer. This has the prefix kilo in front of the unit meter. Kilo means 1,000 or 10 to the 3. So 1 kilometer is an abbreviation for 1,000 meters, or 10 to the 3 meters. So these are the metric prefixes, and you should learn these, all of them. Now, we're not going to use all of them a lot, but they're in your book, and so you should memorize them. Kilo, centi, milli, micro, and nano are the ones that we probably use the most. We also run into mega occasionally. Those are the most common ones. If you can't get it together to memorize all of them, at least memorize those ones I put lines next to. Want to point out that some of these have, oops, that's not a pointer. Some of these have capital letters. Those tend to be the ones that make things much, much larger. Mega is a capital M. It stands for a million, 10 to the 6. Personally, I find it easier to memorize the power of 10. Most of these go by threes. So here's 10 to the 3rd, 10 to the 6th, 9, 12, 15, 18. It's going up by 3. And these go down by 3. Mega is a capital M. It makes it bigger. Milli is a prefix that also starts with the letter M. It's a lowercase m. It makes the unit smaller. So it's 10 to the minus 3. Micro also starts with an M. Okay, we used capital M, we used lowercase m. We're out of M's. We're going to go to the Greek alphabet. So micro, mu for micro. And the rest of them pretty much make sense. It's just the first letter. So again, we have to be very precise and use exactly the correct symbol. So 4.5, capital MM. What's the capital M stand for? Mega. So how long is 4.5 megameters in meters? Well, 4.5, mega stands for 10 to the 6. 4.5 times 10 to the 6 meters. What I did there is I took this prefix multiplier, and instead of writing the symbol, the abbreviation, I wrote the number, what it means. And this is a very fast and easy way to convert between metric units. You can't always do it, but it works sometimes, and when it does, it's really nice. Let's look at this one. This is going the other way. 7.13 times 10 to the minus 9 liters. And they want to know how many nanoliters is that? Well, what does nano stand for? 10 to the minus 9. Well, what if instead of writing out times 10 to the minus 9, what if we just wrote the lowercase n symbol for nano? So this would be 7.13 nanoliters. The lowercase n is an abbreviation for 10 to the minus 9. Any questions? We have some derived units. A derived unit is just a combination of other units. Units of speed, miles per hour, meters per second. It's a combination of two units, a distance unit and a time unit. Volume is a measure of space. It is also a derived unit if we use a unit of length. So if we have a cube and we want to know its volume, if this side is L and it's a cube, then all the other sides are L too, and the volume equals L cubed. Well, if we measure that length in centimeters, we get a volume of centimeters cubed. If we measure it in inches, we would get inches cubed. So volume can be a derived unit. Other common units for measuring volume are the liter and the milliliter. I think we all have a good idea of how much 2 liters is, right? So it's one of the things we have embraced in the metric system. We sell soda in 2-liter bottles. So when we're doing calculations and things and we come up with an answer in liters, we should always ask ourselves, is this reasonable? Is it reasonable that my body contains 0.005 liters of blood? Maybe that's not reasonable, right? So good to have an idea of how big that is. So if we have this cube, which is much nicer than the one I drew, and we have 1 centimeter cubes. So if we've got 10 centimeters on a side, that's 10 cubes. And 10 centimeters tall is 10 cubes tall, and then it's 10 centimeters deep. It's 10 cubes deep. How many cubes, how many little cubes are in the big cube? 1,000. Length times width times height. So 10 this way times 10 this way times 10 that way. 10 times 10 times 10 is 1,000. Here are some common units and their equivalents. So this is mostly converting between the English system and the metric system. You do not need to memorize all of these. I'll just tell you the ones that you should know. You should, let's use the highlighter. You should know, that's not the highlighter. Yeah, cross off the things I want you to memorize. You should know that one. An inch is exactly 2.54 centimeters. I want you to memorize that one because we use it a lot. So you need to know that one, and you need to know this one. 1 cubic centimeter is a milliliter. I think I was supposed to talk about something on the previous page, and I'll go back to it in a minute. But if you were to need relationships like this between meters and yards or pounds and grams, those would be provided on an exam. And when you're doing homework, there's this table in the book. A lot of this is in the back cover of your book as well, and you can go ahead and look that up. I don't remember all of those things. It's a waste of brain space to remember all of those. You remember the ones that you use frequently. Let's go back here because I think I missed something. So here, this is going to be 1,000 cubes, right? 1,000 cubes. Each cube being 1 centimeter on a side, what's the volume of each little cube? 1 cubic centimeter. So the volume of each cube is 1 cubic centimeter. So then what's the volume of the whole big thing if there's 1,000 cubes? It'd be 1,000 cubic centimeters. Well, 1,000 cubic centimeters is what we call 1 liter. A liter is 1,000 cubic centimeters. Remember what the prefix milli means? Milli means 10 to the minus 3. 1 times 10 to the minus 3 is 1 over 1,000. 1 milliliter is 1/1000th of a liter. If 1 liter is 1,000 cubic centimeters, and a milliliter is 1/1000th of a liter, then 1 cubic centimeter is equal to 1 milliliter. In medicine, they use that unit as well, but they call it a cc for cubic centimeter. Another derived unit is density. Density is the mass of something divided by its volume. We have an equation for that, D equals m over v. Common units for liquids and solids are grams per milliliter for liquids, grams per cubic centimeter for solids. A cubic centimeter and a milliliter are exactly the same thing, but we tend to use cubic centimeter for solids. So density is a physical property of a substance, and it does depend on temperature. The density of a substance will change slightly with the temperature. A really important idea about density is, actually, is that coming up? Yes, intensive and extensive properties. An intensive property does not depend on the amount of substance. So here I've got my strawberry lemonade, and it's kind of a, ooh, I spilled it and it ran down my arm. Nice. Too early in the morning. It's kind of a pinky purple color. If I poured half of this into another cup, would the color change? No, it would still be the same color, right? The color of something generally does not depend on how much of it there is. Would the volume change if I poured some out and had a smaller quantity? The volume would change. The mass would change. The density would not change. So intensive properties do not depend on the amount. These are things like density, melting point, color. Intensive properties can be used to identify what a substance is. An extensive property depends on the amount of that substance, things like mass, length, volume. You can't measure the length of a metal bar and determine what kind of a metal it is from its length, because you could have all different lengths of the same metal. It doesn't identify the substance. But the density of a metal is always the same whether you have a little bit of it or a lot of it. And the idea of density is where that joke, which weighs more, a pound of feathers or a pound of bricks, comes from. We think of bricks as heavy and feathers as light. But the joke says a pound of each. They weigh the same. Which one takes up more space? Pound of feathers or a pound of bricks? A pound of feathers is going to take up a lot larger volume because the density is lower. Calculating density. This is a word problem, right? Look at all those words. A lot of people have trouble with word problems. And it's not intelligence, it's just how your brain is wired. And so I understand that a fair number of you do not like word problems. I will do my best to help you with them. Word problems in chemistry are unavoidable. A lot of times, most of the words you can ignore. So here, a man receives a platinum ring from his fiancée. Before the wedding, he notices that the ring feels a little light for its size and decides to determine its density. This is a thing a science nerd would do. He places the ring on a balance, finds that it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters of water. Is the ring made of platinum? How could he figure out the volume of the ring? We'll be doing this in lab, I think. If you put water in a measuring container and note the level of the water and then put an object in, what happens to the level of the water? It goes up, right? It goes up in equal volume to the volume of the object that you put in. So he measured the volume of the water, he put the ring in, and the water went up 0.233 cubic centimeters, so that gives him the volume. Is the ring made of platinum? Well, the density of platinum is known, and it's given in this table right over here. You don't need to memorize densities either, except you should know the density of water is 1. That one's pretty easy. So platinum is down here, 21.4. Units are very important. We need the units to grams per cubic centimeter. So I'm going to write that down because my short-term memory is not that great anymore. Density is 21.4 grams per cubic centimeter. A strategy for word problems is to read through the whole thing, then pull the numbers out and identify what they are. So 3.15, and the unit is grams, and then we've got 0.233 cubic centimeters. Now sometimes the problem gives you what that means, and other times the unit is what you have to use to tell what it is. But here, 3.15 grams, it says a mass of. So that's a mass. If they didn't say that it was a mass, we should be able to tell because gram is a unit of mass. The word volume is not used here, but cubic centimeter is a unit of volume. And so this is the volume of the ring. So to find the density, we use the density equation. Density is mass divided by volume. So 3.15 grams divided by 0.233 cubic centimeters. And then the calculator is going to say 13.5193133. We have to write down the units as well. None of those units cancel out, so they just carry along grams per cubic centimeter. I haven't talked to you about significant figures, so I'm not doing them right now. The density of platinum is 21.4. The density of this ring is 13.5. Is this platinum? Nope. Because a piece of platinum, no matter how large, will have the same density, 21.4. It's an intensive property. It can be used to identify a substance. Questions? The woman in this example is shocked that the ring is fake and returns it. So we're glad to know that she wasn't, trying to cheap out on him. She buys a new ring that has a mass of 4.53 grams and a volume of 0.212 cubic centimeters. Is the new ring platinum? Well, we need to calculate the density. Density is mass divided by volume. So here, it's telling us mass of this, volume of that. So we'll put the mass in, 4.53 grams. And we're going to divide by the volume, 0.212 cubic centimeters. This is what's called showing your work. You should always show your work. It's an important skill. I know that many of you can get the correct answer without writing it down, but in science, it is very important to be able to write down how you got something so that someone at a later time in a distant place could look at your work and see, oh yeah, that's all correct. 4.53 divided by 0.212. Calculator says 21.36792453 grams per cubic centimeter. Is this platinum? Yeah. It didn't come out to be exactly 2.4, but it's very, very close. Any questions?